Welcome back. Today we're going to be looking at topic 1.5, exponent laws. Again, let's start with our learning targets. So by the end of today's lesson, you should be able to use exponent laws to simplify expressions and also solve problems using powers or radicals. Now, today's lesson is intended as an introduction to exponent laws. It's just a refresher on some of the laws that you should already know. As we go on to 1.6 in the next topic, we'll start looking at more complicated examples with exponent laws. So the first law that we're going to talk about is the product of powers. So we're going to start by looking at some examples. If I have 2 cubed times 2 to the 4th, that's going to be 2 to the 7th. If I have 3 over 4 to the 5th times 3 over 4 to the 2, that's also going to be 3 over 4 to the 7th. If you notice here, 2 cubed and 2 to the 4th both have the same base. So our exponent laws are only going to apply if we have the same base. So when we're talking about the product of powers, another way to remember it is that when you multiply powers, you add the exponents. Now, when we say multiply powers, that means that we're multiplying powers with the same base. So for all of these laws, there has to be the same base. A general rule that we can write out as a formula, if I have a to the m times a to the n, that's going to give me a to the m plus n. Now the next rule is quotient of powers. If you look above, it says when you multiply powers, you add the exponents. When we are dividing powers, we're going to subtract the exponents. Now again, that means that we're dividing powers with the same base. So if I have negative 6 to the 8 divided by negative 6 to the 5th, that means negative 6 to the 8 minus 5, which is negative 6 to the 3. Now it's important if our base is negative that we keep that base in brackets because that's telling me that the exponent applies to the entire base and not just the 6. You will notice on your calculator if it's an odd exponent, it's not going to change your answer in the calculator, but if it's an even exponent, it does matter. Now for 7 to the 9th over 7 to the 7th, that would be 7 to the 9 minus 7, which would be 7 squared. All of these can be checked on your calculator if you wanted to verify your answer. So the general rule would be if we have a to the m all over a to the n, or we could write it as a to the m divided by a to the n, that would be the same as a to the m minus n. So we're dividing powers with the same base. That means we're subtracting the exponents. Moving on to our next rule, we're talking about the power of a power. So when you raise a power to a power, you're going to multiply the exponents. So if we have 2 to the 5th raised to the exponent of 3, that's going to be 2 to the 5 times 3, or 2 to the 15. If we have negative 3 squared and then raised to the 4th power, that's going to be negative 3, don't forget the brackets, raised to the 2 times 4, or negative 3 to the power of 8. Again, this is an example where if you put negative 3 to the 8 without those brackets in your calculator, and you put negative 3 to the 8 with those brackets, your answer will be different. So when we take a look at our general rule, that's going to be a to the m raised to the nth power is going to be a to the mn, or a to the m times n. Now those first three rules are our standard rules. We also have the power of a product and the power of a quotient. These are just rules that are extensions of the ones that we've already applied. So for power of a product, I'll give you a smaller example here, x squared times y, and then we're going to cube it. Well, what that means is x squared y times x squared y times x squared y. Notice this is just our product rule. So we have x squared times x squared times x squared. If I'm multiplying powers with the same base, I'm going to add the exponents. That's going to be x to the 6th. If I have y times y times y, that's y to the 1 times y to the 1 times y to the 1. That's going to give me y cubed. But I could also just look at the power of a power. This is x squared and then cubed. So that becomes x to the 6th because 2 times 3 is 6. And y to the 1, 1 times 3 is 3. So as we look at these examples, we could be thinking about this as distribution. When we look at this first one here, we've got a squared and then cubed. So that 3 is going to distribute to both the a squared and to the b to the 5th. So this becomes a squared and then cubed. So a squared raised to the 3rd power, which would give us a to the 2 times 3, so a to the 6th. And then 5 times 3 is 15. So this is b to the 5th raised to the 3rd power is going to be b to the 15. Now, when we start introducing numbers, sometimes it gets a little bit tricky because we just want to go 4 times 4. But if you remember, numbers also have an exponent. If I have 4, that means 4 to the 1. So I'm still distributing that exponent. 4 to the 1 raised to the 4th power. A cubed raised to the 4th power. B squared raised to the 4th power. So that would give us 4 to the 1 times 4, which is 4 to the 4th, and then a to the 3 times 4, so a to the 12th, and then b to the 2 times 4, which is b to the 8th. You can go one step further and evaluate. 4 to the 4th is 256, so we have 256, a to the 12, b to the 8. When we're writing our general rule, we're going to have a to the m times b to the n, and we'll raise that to the pth power, which is going to give us a to the mp times b to the np. So we're distributing that exponent to all the exponents within that bracket. Now, when we're moving on to power of a quotient, this is basically the same thing as power of a product. It's just that our term is written as a fraction and not as a multiplication statement. So I'm still going to be distributing my exponents throughout. And again, if I'm looking at numbers, I'm going to remember that that number has an exponent of 1, and that's really important. Especially in the beginning, it's probably helpful to write those exponents in. So here we would have a to the 3 times 3, so a to the 9, and on the bottom or in the denominator we have b to the 5th raised to the 3rd power, so b to the 15. And with the number here we have 2 to the 1 raised to the 3rd power, so 2 cubed, a to the 6 times 3, so a to the 18, and then we have 3 to the 1st raised to the 3rd power, so 3 cubed, and then we have b to the 12, so 4 times 3 is 12. And once again, you can go through and simplify. 2 cubed is 8, so we're going to have 8 a to the 18. And then on the bottom, we've got 3 cubed, which is 27, 27 b to the 12. So if we're writing our general statement, we're going to have a to the m divided by a to the n, all raised to the pth power. We're going to have a to the mp divided by a to the np. So our last rule is the exponent of 0. Anything raised to the exponent of 0 is 1. So 2 to the 0 is 1, and this messy term here raised to the 0 is 1. It doesn't matter how messy everything is inside. If it's all bracketed and there's a 0 outside as an exponent, it's equivalent to 1. Now you might be wondering, well, why is that? Well, let's take a look at an example and use our earlier exponent rules. If I have x squared divided by x squared, that's going to be 1 because anything divided by itself is 1. But if I use my exponent rules, when I'm dividing powers with the same base, I'm going to subtract my exponents. That would give me x to the 2 minus 2, which is x to the 0. Well, if x squared divided by x squared is 1, then x to the 0 must also be 1. So our general rule is a to the 0 is equal to 1. Now, when we're looking at the exponent of 0, it's really important that we take a look at where that 0 is applying to. If you look above, I had 3mn squared divided by 7, p to the 6th, q to the 4th, all in brackets, and then put to the exponent of 0. That equaled 1. But down here, I have 5 and then a bracket, mn squared, close the bracket, raised to the 0. That means the 0 is only applying to what's in the brackets. So this part in the brackets is 1. But the 5 is outside of that. So that is actually 5 times 1, which is 5. So just be very careful to look at where that 0 is applying. Okay, so that was a refresher on our exponent laws. We're going to be using those a number of times throughout the semester, and we're going to start looking at much more complicated combinations of those exponent laws in later lessons. But I just want to make sure that you have a good foundation on the basics first. So we're going to move on and take a look at 3 examples here that are involving word problems where we're using those exponent laws. Now, in the real world, we are using exponents a lot of different ways, especially when we start looking at chemistry, biology, physics. We're going to be using scientific notation, and we're going to be working with very large numbers. We start talking about space. If we start talking about cell size or cell division, we have to be working with very big and very small numbers. And so that's where you're often going to see exponents. As you move into other high school courses like grade 11 and 12, we'll start talking about compound interest. We'll be talking about earthquakes. and sound waves and all of those types of things, you're definitely going to start working with bigger numbers. So we're just starting with the basics of exponent laws and just starting to look at ways in which they can be applied. So it's really, again, important that you have that foundation of the exponent laws, and then we'll work on applying them as we move forward. So our first example here, it says it is estimated that there are 117 billion grasshoppers in an area of 39,000 kilometers squared of Saskatchewan. Approximately how many grasshoppers are there per square kilometer? Well, one way to do this is to just write out 117 billion. So that's going to be 117 and 9 zeros. And that's divided by 39,000. So we can just do the math. Well, the first thing I'm going to do is just go about getting rid of some zeros there. And now I'm left with 17 million divided by 39. So on my calculator, I can go 117 million divided by 39. In this case, I probably can put the whole amount in, 117 billion, and divide by 39,000. I'm still getting the same answer. So if you notice there, I've got 3 and 6 zeros, so that's going to be 3 million. The reality is, though, our calculators can't always work with really big or really small numbers by just entering them all in. Plus, who wants to type in like 25 zeros? So we can often write things in exponential notation, and that will help make entering it into our calculator and evaluating a little bit easier. So when we consider 117 billion, that's 117 and then 9 zeros, or 10 to the 9. So we're going to have 117 times 10 to the 9. And on the bottom here, we've got 39,000. Well, that's 39 and 3 zeros, so 39 times 10 cubed. Well, on my calculator, I can go 117 divided by 39. That's going to be 3. And 10 to the 9 divided by 10 cubed is going to be 10 to the 6th. And if you remember, 10 to the 6th is a million, so this is just 3 million. So a way that I can calculate it a little bit quicker, and again on my calculator, it's fairly quick to put 117 divided by 39 in my calculator. Example 2 says the Great Galaxy in Andromeda is about 2.2 million light years from Earth. Light travels at about 5.9 trillion miles in a year. The question is, how many miles is the Great Galaxy in Andromeda from Earth? So when we take a look at solving this question, we have to decide how are we going to calculate it. Well, we have a rate of 5.9 trillion miles per year. And so in this case, we're talking about a light year. And we have 2.2 million light years. So I'm going to take my light years and I'm going to multiply by miles per year so that my light years cancel. Now again, these numbers are quite large, so it might help to write them as exponential notation. So we're going to have 2.2 times 10 to the 1, 2, 3, 4, 5, 6, so 10 to the 6th. Again, that could be written as 2.2 bracket 10 to the 6th. And that's all being multiplied by 5.9 trillion. So that's going to be 5.9 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And again, that can be written as 5.9 and then 10 to the 12. So using our exponent laws, because we have 10 to the 6th and 10 to the 12th, we can combine those. So all we need to do on our calculator is 2.2 times 5.9, which is 12.98. And then 10 to the 6 plus 12, which is 18. So that would be 12.98 times 10 to the 18 miles. And typically we would write that in scientific notation. So we're just going to move that decimal 1 over. So it's going to be 1.298 times 10 to the 19 miles. And one final example. Quite often when we're working with exponents, we're going to be working with different types of formulas. And so for this example, it says wildlife biologists are tracking the whooping crane population growth at Wood Buffalo National Park in Alberta. The crane population increased by a growth rate of 7.3% per year from 2002 to 2008. There were 174 whooping cranes in 2002. The rate of growth can be modeled using this formula. Now, when you get to grade 12, you'll actually be looking at building these formulas yourself. For now, we're just going to work with the formula as given. So the population is 174 times 1.073 to the n. P is the estimated population and n is the number of years. Now, it says how many whooping cranes were there in 2000? Well, if this is our population in 2002, and we're being asked for our population in 2000, we're actually being asked for our population 2 years before. Now, we haven't looked at negative exponents yet, but if we're looking at 2 years into the past, that's exactly what we want to do. We want to use a negative exponent. So my formula, if it helps, you can always write off to the side. My population is what I'm looking for. My n value, since it's 2 years in the past, is going to be -2. So my formula is 174 times 1.073 to the n, and then I can plug in my information. So 174 times 1.073 to the exponent -2. At this point, you are perfectly fine to put it into your calculator. So we would type 174, open our bracket, 1.073, close your bracket, and then exponent -2. Now notice your negative is down here on the bottom, not up here. That's your subtraction side. And so you should get 151.1296. And because we're talking about the population of the whooping crane, we're not going to have 1.151.1296 birds. We're going to have 159 cranes. Now for the second example, it said, if the conditions remained ideal, how many whooping cranes would you expect there to be in 2025? So the first thing we're going to need to do is figure out how many years are there from 2002 to 2025. So if we take 2025 and we subtract 2002, that's going to give us 23 years. And so that's going to be our n value. So our population is still unknown, and our n value is 23. So our formula again, 174 times 1.073 to the n, we're going to have 174 times 1.073 to the exponent of 23. So again, we'll move to our calculator, 174 bracket 1.073, close your bracket, to the exponent 23. And we're estimating about 879.7, so about 880 whooping cranes. Now, as I mentioned earlier, you will be working with these exponential formulas in grade 12 in both 30-1 and 30-2. So I just want you to take one quick look at that formula. We have P equals 174 times 1.073 to the exponent of n. This is going to be a little bit of a cliffhanger, but I want you to take a look at the formula and see if you can figure out where those numbers are coming from in the formula. Where is the 174 coming from? Where is the 1.073 coming from? I'm not going to tell you today because you're going to be learning about this in grade 12, but when you start seeing formulas in grade 10, I want you to think about where those numbers are coming from, because as you move into other years of high school, you're going to have to start building those formulas yourself. If you can start recognizing the patterns now, imagine how much easier it'll be when you have to build them yourself in a couple years. All right, that's all I have for you guys today. Hopefully you have a good understanding of exponent laws and you've had some practice with some of the applications. Have a great day. We'll see you soon.